discuss it after class. Okay. The image last week we discussed about we talked about spatial variability and temporal variability in the properties, how properties differ based on your location or position, and how the properties differ based on time. So some of the properties depend on the position, while some of the properties depend on both position or time or something. I'll give you an example. So example, if you have, see, I wanted to mention that I go through with the week's lectures because it's not like I am thoroughly covering everything, but I want to give you people an intuitive understanding of like not just reading the concepts from the book, but trying to understand what is happening. And unfortunately, well, when I was in my bachelor's, I did not get that intuitive feeling, and I had to gather a lot of resources. But now that I feel that I have an understanding about the what's behind, so that is why I go over with the lectures over all the major topics. Maybe there is something intuitive that I can impart, that I can mention, and that may help you visualize and understand the concepts more. Otherwise, we can only have problem solving sessions. That is also fine by me. So I was saying that we have the properties of soil are they can be dependent on, they can be time dependent, they can be space, they can have space dependency. So how is it that properties change? Some of the properties are simply characteristics which do not change with space or time. For example, we will take specific gravity, inorganic soil. No matter what position, no matter what time, unless and until the time is so long that some kind of soil degradation is taking place, uh, this will not change over time, this will not change over space. But properties like, let me say, permeability. I have a soil here, and the soil that I have here has a self weight of H, then this will be H2. If I divide it in layers, imagine that I divided it in very small layers. So this will have a higher weight over it. This will have a lower weight over it. Confining stress here is more. And with more confining stress, your your void ratio will be low here. Void ratio as you go towards the surface will increase. The void ratio as you go down will decrease because of the presence of this load here. And as the void ratio decrease, yes, okay, as the void ratio decreases, so does the permeability. What we do in classical soil mechanics, usually what we do is we assume that this layer has a permeability of K. We assume a constant permeability. But in actuality, especially let us say, for example, when you are constructing a dam, you construct the base and you compact. Then you construct another layer, you compact. You construct another layer, you compact, isn't it? So what happens is that the first layer receives multiple uh, compaction efforts as compared to this layer. It will receive one less, this layer will receive one less. So you cannot say that you have compacted this dam or embankment to a uniform uh, relative density. This density will always be high. So in that condition, what you get kind of a stratified deposit, and this stratified deposit has a different permeability in this direction. It has a different permeability in this direction. It has maybe different properties in x and y direction. That is why in seepage nets, when you study the anisotropic seepage net also. It is because uh, the way the dams are, these embankments are constructed, you get a stratified kind of deposit that may have slightly different properties. It does not have same properties. So as you see, based on the position, the property is changing, isn't it? So in a field, if you want to model this, if you want to understand what will be the permeability here, so you have to take into account the location or the position of this property, which is why we develop these seepage nets, we develop these flow nets. So space dependency is dependency of the property on x and y coordinates. And this is already a multivariable problem here, isn't it? There are two variables here. And to get the solution for this, you will have to go for partial differential equations. And partial differential equations is what basically seepage net, but we write x del square x by del del square h by del x square plus del square h by del y square equals, we like the streamlines and the equipotential lines like this. Now, time dependency is uh, comes into play when we talk about consolidation. So basically, uh, this is about the interaction of your permeability and let us say time with time. In in last class I defined. So, for example, let me assume that permeability is not changing with time. I'm saying that the property is dependent on the permeability. So, what depends on time is the head, hydraulic head. Okay, permeability does not depend on time here. The hydraulic head depends on time. You have a layer of clay that has a very low permeability, and suddenly you load it. Okay, as you load it, I actually discussed this in last class. You have these soil contact uh, contact spaces on which the load will directly. So the load transfer mechanism in the soils is through the grain to grain contact. Okay, okay. But you know, in a spring, if you pull this spring, in order for the spring to uh, mm, absorb the force that you are uh, inflicting on it, it will stretch. So you will see displacement. So you need this displacement for the spring to absorb the force you have put on it. In the in the same manner, if we talk about soil, think about it as a system made up of springs. If I put in a load on this, which is greater than the like okay, if I put a load on this, it requires that the the system requires that the soil compresses under this load, unless and until it is so stiff that there is no uh, movement at all. The system requires force equilibrium requires that there is a displacement here for the load to be transferred to all these strings. But only if we talk about springs, then we can think of how it is happening. But since soil is a porous medium, it is not, uh, this is something that happens in solid mechanics. In soil, especially if uh, this is your unit volume, let me say, and it's saturated, you will have soil here and you will have water here. Basic assumption, basic assumption of our theories is soil is incompressible, water is incompressible, and given that this is saturated, for this displacement to take place, you need the voids. Basically, you need the water from the voids to move out so that the volume of voids may change. And this movement of water depends on the permeability of the system. If the permeability is very low, then instantaneously if I load it, what will happen is that the pore water in this scenario, which is present on this in this system, will take all the load. Okay, and as the water moves out, as the water moves out, you see displacement, and as uh, instantaneously you will let me show you here. So instantaneously at time equals 0, if this is your soil sample, this is the height of the sample, and you are loading it, what you will see is that all the load that you have uh, uh, throughout the system, first at t is equivalent to 0, you will see exactly the load that you have provided, that you have imposed on the system. But then uh, then with time what happens is that your water flows out, and now your load is getting transferred to your soil skeleton. So this is the excess pore water pressure. This is not the pore water pressure. This is the excess pore water pressure that in at time equals 0 is delta sigma, or how much you have uh, imposed, and with time it slowly dissipates. And how this dissipation takes place is what basically we study in your consolidation analysis. And we talked about mathematical expression of uh, u is the a degree of consolidation. Usually you will see that we often talk about we talk about degree of basically when we say degree of something, what we want to measure is how much of the phenomena has already taken place over how much of the phenomena is possible. For example, if we talk about, let us say, sometimes we talk about effective volumetric water content. That's not a good example. But okay, I'll give you an example of degree of uh, consolidation. Degree of consolidation basically tells you if in a system you know that possibility for uh, the volume change is only because of volume of voids, isn't it? So if the total volume of voids initially is EI, then the total possibility of change will depend on EI, isn't it? And EI naught, or total. Then degree of consolidation will basically tell you uh, what is the void ratio when you compare it with what it initially was supposed to be greater, yeah, uh, ei minus ei naught minus e over the total void ratio change that you will see in the system, and E is the present void ratio change, Ei naught is so how much consolidation has taken place over how much consolidation can take place. And you will see this kind of an equation in many things, but right now I can't remember uh, other things, but I remember that there was some things in which you need this. Okay, so this is the relationship between U and T. It's the So the compressibility of soil we talked about. We talked about solution to the compressibility equation is like this, in which Ui is the initial excess pore water pressure uniform over the whole depth. M is equal to 1 by 2 pi plus 1, where M is a positive intrinsic value from infinity. T is CVT by H. Then is not of 0. So this, as I was saying, you for a particular point, degree of consolidation will be equal to ui minus uz over ui. So this is the initial excess over pressure of final minus present over final. Final is supposed to be 0, otherwise you would have ui minus 0 here. Okay. So you get a relationship between u and t. Talked about river drainage last time.
Do you want other equation, madam?
Yeah.
You want another equation for degree of
No, no,
consolidation?
no, 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 no. I'm
No.
going through this compressibility of soils and checking that anything else I would like to discuss upon. No. So
Okay.
maybe we can do some questions then, because I could not find any. Okay, just a moment. This is 6. check. Give me 5 minutes, please. I'm not able to find that presentation in which I had some questions about consolidation. I can actually this is from my previous session, as in last year, where I discussed the consolidation. I think I discussed it in a better way last time. Uh, and I think that is what I discussed in consolidation, not more the, not beyond that. Now we will move forward from consolidation after discussing this. Okay. So from Trazagi's 1D experiment, you know, that we assume, let us say that this is a structure like a porous material, and we imagine that the springs, that the solid skeleton is like a series of springs, and then you impose a load of delta sigma. Uh, so at time t equals to 0, you will have an excess pore water pressure equal to delta sigma before loading at t equals to 0. Loading at this. So the total stress increase at time equals to 0 will be equal to delta sigma here. Pore water pressure will be equal to delta sigma here, but excess pore water pressure will not increase instantly. And then as time progresses at t is equivalent to t, the total stress will remain same, but the excess pore water pressure decreases. See, it's decreasing, and it's decreasing in such a way that the load transfer from this is taking place, and uh, the load transfer from here is going over to the soil skeleton, which is the effective stress. Okay, and then at t equals to infinity, you will have a zero excess pore water pressure, and you will have a completely loaded soil skeleton. And uh, that is what we try to do. These are called the isochrones. At different times, we try to calculate what is the pore water pressure throughout the depth. So your consolidation or your uh, uh, what is it? The hydraulic head is both space and time dependent. If you see that if if this is a double drainage system, what will happen is that the uh, particles or the areas that are nearer to the drainage layer will dissipate their excess pore water pressure immediately. And that is why what you see here is that at t equals to 0 and just like 1 second or 2 second, what will happen just at the boundaries, excess pore water pressure will dissipate, and you will get a higher effective sigma, and your pore water pressure will become lower. And if you follow these lines of excess pore water pressure uh, at different times. For example, you take photographs at different time stamps. You take photographs of a system of uh, um, the what was that called? Pipettes? No, standpipes. You connect your system to a standpipe and you load it, and that at different points you take these snapshots. So you will have the um, at same time isochrones at same times the distribution of pore water pressure throughout the depth of the sample, and it will not be same. And this is what your equation of consolidation basically gives you. It gives you the isochrones. So your equation in your equation you can see that your head uh, hydraulic head is dependent both on time and space. So U is equal to CV del square U by del X square. Okay. So we use these three quantities, which is the degree of saturation, the depth ratio, and the time, this time TV. What we do is we use these. What we have done is that we have made charts based on the isochrones. We have made charts for different HYZ and different TV, different UZ, so that you calculate these quantities for your soil. Okay, you calculate these quantities, and based on these quantities, you look at these charts and you get to calculate your excess pore water pressure or hydraulic head. And from that hydraulic head, you can calculate your permeability, you can calculate your flow through the material and everything. So this is the exact usage of the equation. It is not to uh, define or calculate any property. The uh, purpose of the equation is for you to simulate or understand or predict the flow taking place through a uh, soil. And it is not only about the flow that is taking place through the soil, you also need this because when you are loading and you are loading clays, if you have a clay strata, you need to know what the excess pore water pressure will be over this material and how long it will take to dissipate or how long it will take for effective strength to regain, because that is what you need when you are building foundations even, isn't it? So that is what this all this topic is about, and we can move on to our next topic. uh, is there something else you want to discuss? Yes, please.
Madam,
Yes.
the spring analogy technique,
Yeah.
is it applicable only for loading or even for unloading also?
String analogy. Let me think about. No, it can be applicable for uh yeah, for unloading. Yeah, it can be applicable for unloading, but it will only give you the elastic part because your springs are linear elastic, but your soil behaves in an elastic plastic manner. And when you load your soil, you see that after you remove your load, you will see some rebound back, but the plastic, show you thing. So in soils, if you plot your, okay, so if you plot your void ratio with your, let's say, log of sigma, you know that you get this kind of a behavior for NC soil, isn't it? And if it is OC soil, you will get something like this. Okay. So basically, uh, what happens is that when you unload, the let's let the slope of this unloading line be, of this line be kappa, and the slope of this line be lambda. Okay. So what happens is when you unload, you only unload the elastic part, even though during loading, if I, let me say that initially my load was here and I gave a delta P, and now my load is here. So I see a void ratio change from E1 to E2. But when I unload it, it will not go like this. It will move something like this. Okay. So when it's moving like this, uh, obviously it will not go to zero. If I, for example, move it back to P, it will move like this. And now my E will be less than E2, but it will be greater than E1. It will not be equal to E1. This is the part of uh, deformation that I got back. So this is the elastic part. This is the plastic part. So when you are talking about the soil analogy, see, this is elastoplastic, but this is only elastic because you are recovering back your elastic strains. So when you're talking about your soil analogy, in your soil analogy, if you assume that unloading uh, brings back the springs to their original uh, form, then you are only taking the elastic part. However, it will also mean in that sense that a negative pore water pressure is getting there. If you loaded the springs here and you had a porous material here, now when the springs want to release, water is to move inside, which is negative of what we were doing. So we will have a negative pore water pressure. So I would rather uh, that the analogy be taken only for loading, not for unloading.
Yeah, even I am thinking because there is an exit facility only for water, but there is no re-entry into the um, container. That is
Yeah,
why I am
no,
thinking whether it's possible or not.
yeah, this is just a thought experiment, है ना?
Okay.
This
Mhm.
is just a thought experiment. But in
Mm.
real life, you will see some rebound back. And
Yeah,
if you
that is okay. Madam. Real, this left-hand side, what you have drawn the graph is very clear.
okay,
But is this applicable in Teresa's spring model or not? That's what my question.
yeah, it is applicable in Terzagi's model, but not in this form. As in, I'm saying that Terzagi's model, we use, what do we use it?
Okay, most Indian have not many books.
I can't hear you. I can't hear you.
Uh, but I have not found original books of geotech. That's why
Arav,
I'm
your
asking.
voice is really breaking. Hello?
Uh, yes, madam. Is it clear, madam? Now, madam,
Yeah,
can you hear?
it's yes, yes, I can hear now. Yes, please.
Yeah, I saw in most of the test books about only loading,
Yeah,
particularly spring analogy model. I didn't see it in unloading case.
yeah. You spring analogy we will not extend, but Ragi's 1D model we extend by using UC, CC, and CR. We differentiate the slopes of the loading and the unloading line.
Yes, madam, it is clear, madam.
Okay, so in that sense we can take it, but okay. So next we will. Any more questions? We can go on. Let's discuss about the earth pressure theory. We were still talking about compressibility of soils. Okay. So when we talk about earth, let's talk about earth pressure theories. So what is earth pressure as such? You know, in hydraulics, we study that there is a dam and there is water behind this dam. So based on this hydrostatic loading, what will be the load behind this? Why? Because something is being retained behind the structure. We are trying to block the escape of this material. Okay, we're kind of barricading it. Same thing happens when we build earth retaining structures, which means that you build structures, embankments that are like your uh, earth water retaining structures. You build structures to retain earth or soil, and where you might need to do something like this is, for example, if you have, let me say that there is a mountainous path and you have cut through a mountain and you have built this road through the mountain, and it used to be something like this, and now you have gone and removed this soil and made a steep cut here. So all the load from above can lead this slope that you have created here to fail and just fail like this. So what you do is when you do this kind of construction, you want to retain this. so that no earth flow or debris flow takes place. This is one case. So here you either go for a retaining wall, you go for different methods. Other thing is that you have, for example, let's say that this is a sloping kind of. I have a sloping kind. I bought a land in a sloping kind of area. Okay, and this is my property line. This is the property line of my neighbor. Okay, so when I do excavate, cutting and filling kind of work, I don't want to. I don't want my land to be like this. My house is here, for example. Then, so what I do is I kind of level it, and in this process, I'm taking this off. So in this process, I have created this steep slope here, kind of a vertical. I need to retain it so that this does not flow. And similarly, someone else might create these kinds. Other thing is that you might temporarily need uh, some kind of a retaining structure. For example, when you are building during large constructions like an abutment for a bridge. So, in an abutment for a bridge, you know you have to construct it underground. And for you to construct it underground, you need to excavate this whole area first. You have to retain these walls so that they don't collapse. You have to create an area in which the construction workers may work and build the foundation of this bridge pier, and then you remove these temporary walls and you fill in the soil back. Same is the case when you have construction like uh, for example, you have metros. When you see those uh, sheetings along wherever you are constructing, you will see bracing on the. So it's basically these are the structures which we call as earth retaining structures. So what we will study in earth retaining structures is what kind of force these structures may uh, so because this uh, force is not about the structure itself. We are not studying the design of the structure, like how we should design the structure so that it will not fail. But we are trying to understand what loads the structure will uh, feel based on the soil that is retained behind it. So, if you were a structured if you were a structure student, you would have simply studied about the structure strength, the concrete, the reinforcement, because that's their job. Our job is, and they would have simplified, they would have just said that this is the load that is coming on the structure, you design the structure. But our job is to tell them what is the load that is coming on the structure. Okay. So like in water, I mentioned this earlier also, you have a hydrostatic loading because water has a neutral loading, and if this was H, this was gamma H, and you used to have a total load of this area half of gamma H. square. But soils are different in a sense that they have different stress, we can say mechanism, not mechanism, but distribution in horizontal and vertical directions. So basically, up till now, whatever, whenever we have talked about overburden. We are basically talking about the burden on the weight over the point, isn't it? So in this direction, we know that this will be gamma b times h. The load here will be gamma b times h. But what about the, if I remove this, what will be the load acting in this direction? So obviously right now it is in equilibrium, but I want to understand how much. So this always is uh, the horizontal stress is a portion of your vertical stress. It is not equal to equal. It's not one is one relation. So the this is k x times sigma horizontal or vertical. So at any soil point you will have a vertical stress and horizontal stress, such that sigma h by sigma b is equivalent to k. This is your earth coefficient. Now, what the formation of this earth coefficient is depends on if you are if you're having an active, passive, or at rest state. So think about it. This is like it's like a door. Okay. So when you're pulling it, you this is like a passive mode. When you're pushing it, it's active mode. And when it's at rest, when you're not doing anything, then it's at rest. So basically, what it means in geotechnical sense is at rest, as in there is no movement of, let me say that there is this building, there is this foundation, and let me say, for example, there is a pile foundation. I want to calculate the lateral pressure here, and I know that this is completely in equilibrium. There is no uh, active or passive, there is no movement of this structure with respect to the soil, or the soil with respect to the structure, such that this is at total complete rest. This is called the K naught condition. Just at rest. Soil is not failing uh, in any way. Now, as opposed to this, I have a structure which is holding some soil here. You see, there is an imbalance of forces on this structure. There is a force that is acting in this direction, but not in this direction. If this was completely confined, it would have been at rest, but it is not. There is an active force that is pushing the structure to move like this, such that if the structure moves like this, the soil will go down and in. This is the active failure. But if the case was such that I was pushing this from here such that this was moving in towards the soil, this would have been a passive earth pressure. So we would have had uh, so types of retaining structures, gravity, wall, and earth pressure. Uh, so active earth pressure, passive earth pressure, and earth pressure condition at rest. So if you see here, uh, first I told you about what is earth pressure. Earth pressure is just the ratio of your vertical and horizontal stresses is your earth pressure. Now, based on the condition you are in, you can have an active earth pressure, passive earth pressure. Uh, Wall movement required to reach active pressures. So the active pressures, if you see, you need smaller deflection for, how can I mention? So movement away from backfill, as we mentioned here, will give rise to active earth pressure. Movement towards backfill will give rise to passive earth pressure. And wall moves out, wall moves in. Shear stress on failure plane reduces. We can see this later based on Rankine's theory. Shear stress on failure plane increases, lateral pressure reduces, lateral pressure. If you see here, as you as this moves out, there will be more there will be a relaxation in the confining pressure of this failed zone. While here the confining pressure will increase because I am providing some force here. Okay. So K naught is just sigma h over sigma v, and it can be given as 1 minus sine phi more circle at rest condition. So what we are doing is at rest you will have a, let us say I take a sample, this will be the sigma v, this will be the sigma h. Okay. If sigma h over sigma v is your K A or Kp, so you see if Ka is greater than 1, you will have sigma h is greater than sigma v. And if Ka, let's not call A by B, is less than 1, sigma h will be less than sigma v, isn't it? then your sigma h will be your sigma 1 and sigma v will be your sigma 3. While in this case, sigma h will be your sigma 3 and sigma v will be your sigma 1, because you know maximum and minimum principal shear stresses are based on the magnitudes. So you will have uh, this is always sigma 1, sigma 3. You will have a sigma h, sigma 3, sorry, sigma v, or KAP greater than 1, and sigma v, sigma h for KAP less than 1. Uh, yeah, lateral earth pressure, active phase, passive sliding friction, failure plane. This is the passive earth pressure. The wedge moves out and up. More surface of passive pressure. See, you see here for active condition, this is sigma v and this is sigma h. And we saw that if your sigma h was greater than sigma v, or sigma h was less than sigma v, which is your active condition, you will have sigma v here and sigma h here, sigma v here and sigma h here. And in passive pressure, it's the opposite. You have sigma h here and sigma v here. Okay, so basically, okay, this is the one. Um, Here, if you see, let's say you have this active condition in which your sigma h is less than sigma 3. Okay, this would be your failure like this. Should be- Let's call this h, sigma v, sigma v. So in this case, your sigma h is less than your sigma v, and in this case, your sigma h is greater than your sigma v. This will be the case for your passive pressure. This will be the case for your active pressure. But this is not what I wanted to mention. I forgot. There was this You change the sigma 3, it increases. Let's see.
Center was sigma vertical, madam. Only center was sigma vertical. Remaining will be sigma horizontal both.
Without the same, uh, okay. So this is for passive, this is for active. Okay. I'm actually not able to remember what I intended to mention with this. Okay.
It's okay.
So this is the granular backfill. This is the H. You know the sigma 1 will be gamma H. And here sigma 3 will be K times gamma H. And okay, this is the thing that I wanted to mention with it. But the angle of failure plane based on if it is active pressure or it is passive pressure. So sigma 1, sigma 3 here, plus 5, 90 minus 5. Okay, so basically in your active phase you will have this 90 plus 5, which will be equal to this. Basically, the derivation I have barely forgotten about, but we know um, from the Moore that we can basically how we calculate the value of Ka and Kp. K is 1 minus sine phi over 1 plus sine phi, while Kp is 1 plus sine phi over 1 minus sine phi. Kp is always greater than Ka, as you can see from the formulation itself. Uh, 1 minus sine phi over 1 plus sine phi. Basically, this will always be less than 1. So your value here, this will be between 0 to 1, and thus this itself will always be less than 1, and this will be greater than 1. And when you recip uh, calculate the reciprocal, you will this will always be greater than 1. Like this will always be greater than Ka because you have taken the reciprocal of while something that was less than 1. Okay. And the next thing is that okay, this is your simple retaining wall. What will be the loading on this wall? So the loading on this wall will be in this direction. So what we do, and let us say that it has a water table here. What we do is we calculate the height Yes, please. So we calculate the depth Z. If it is H1, you know this will be gamma 1 H1, the vertical stress, the sigma 3. And then you here it will be effective stress will be gamma 1 H1 plus gamma 2 gamma submerged. So this is the effective vertical stress. The effective horizontal stress will be sigma 1 is equivalent to Ka times gamma 1 H. Sigma will be Ka. We just have to multiply these with Ka. And then basically what we do is we calculate area of this diagram to calculate the total load that the uh, retaining wall is carrying. So K1H1 gamma T plus KH2 gamma submerged, and this is the load due to the water. Uh, See, why we take effective stress here is why in uh, this is very important that you take sigma vertical horizontal, very important. Why to take effective stresses? Why? Because if you take total stress, like here, what you are doing is, if I take total stress here, if I had taken gamma saturated versus H, what I'm basically and then multiplied it with K, what I'm basically doing is that I am multiplying this K to the loading from both the soil skeleton as well as the water. But you know that water, because of its hydrostatic nature, it has same load in all directions. It will not, it will never be Ka times gamma W here.
Excuse me, madam.
Yes, please.
Screen sharing
Uh,
just now disappear, madam. Screen.
is this okay?
Okay, madam. Okay.
So this will never be Ka of sand times. So the K for water will be 1. Okay. That is why you need to separate the soil skeleton vertical load and the water vertical load and then apply the K values. That is why the K you will always have effective here. If you use it with total stress, you will get wrong values. Okay. So the other thing that we want to mention is the assumptions. This is also important. So you have two theories. You have a Rankine's theory and you have a Coulomb's theory for your earth pressures. So you have a Rankine's theory and you have a Coulomb's theory. Both of these theories give a different set of assumptions, which is where this these theories exactly differ. Is first thing is frictional force between backfill and retaining wall are assumed negligible. What this actually means is that when you make this kind of a free body diagram, if this is the failure angle and you have a internal friction angle of phi and you have this weight here and you have a passive earth pressure acting in this direction, the resultant of these will form an angle of phi with the node. Okay, why? This is the property of your friction angle itself. Okay, but in Coulomb's theory, you take that this uh, frictional force, the angle of friction between wall and this is not equal to zero. You take it as delta. Delta may be something multiplied by तो मुझे बोल रहा है phi, and in this case you get a resultant that is inclined at a different angle based on the frictional angle between your wall and your uh, soil. See, this resultant is inclined at phi, but if you see the Coulomb's theory, this resultant is inclined at this PA is inclined at delta. Sorry, I should have mentioned not the resultant. This PA is inclined at delta. Let me check this. Okay, okay. Sorry, I should have mentioned. What I should have mentioned was I got a little confused with this value, and actually at the back of the uh, fill. So basically, what we are saying is not this, sorry, but this. We are more interested in here, the angle of friction with the wall. So when this is frictionless, you will have a PA that is straight. And also we have also other assumption in Rankine. One assumption was frictionless. Other assumption was straight. There is no incline in the back of the wall. While the Coulomb's theory assumes both uh, that the wall is not frictionless and wall may be inclined. So this inclination that you see here, theta, and if you have a, so this is a frictionless wall. You have an inclination here. Is it mentioned? This is here. Yeah, you see here your PA is inclined because your wall is not frictionless. Here your PA is inclined because your backfill is inclined. See here, you don't have an inclined backfill and you have a frictionless backfill. Then you have a PA that is horizontal. And if you had, let me say, an inclined backfill, you would see a resultant like this. So this PH, you will have a PH in this direction and H in this direction. और फिर उसका हम resultant लेंगे. But the thing that I wanted to mention, you see here, the gravity retaining wall shown uses angle of friction between the uh, wall and the retaining wall and the soil as delta, and Coulomb's active pressure theory determined factor of safety. You see here, you will have delta plus this angle. This angle is 90 minus 75, which is 15. First, you will have this angle because of inclination of the wall. This is very easy to understand. The inclination of the wall is simply we are doing is, say that I have a wall which has an inclination. Okay. Now I want to check the forces on this. What I will do is if this is my coordinate system, I want to check the coordinate at here, isn't it? But I want to check normal and vertical. So I will what I will do is I will simply rotate my coordinate system by these. Okay. So what I have done is I have rotated my coordinate system such that I have a normal here. Okay. Then I have to fix for the angle of friction between the wall and the uh, soil. So then I take delta and then I take the PA. Okay, so in Rankine's theory, you first have the assumption that the wall is straight, and Coulomb's theory tells us if the wall is not straight, what do we have to do is that the PA we have to first incline at whatever the theta is. Then second assumption is that frictionless, which means that your delta is zero. And Coulomb's theory tells us if the wall is rough, you will have a, an angle here again. So you will have to take this angle as delta plus theta. And any more assumptions? The wall is straight and the surface of the backfill is horizontal. Now again, if the surface of the backfill is not horizontal, we will have to adjust this again. How we will adjust that? If the surface of the backfill is not horizontal. was the Rankines theory, and this is your Wolff's theory, in which your testing is also not plane. So you have beta sine phi gamma sin phi phi cos theta if your this thing is inclined, you will have till now what we were doing was we were just taking the failure wedge like this, isn't it? But now we have to adjust for this inclination, and this has been given. The inclination of this failure wedge is initially it was 5 plus 5 by 4, 5 by 4 plus 5 by 2. This was without any this thing, and now it is we have add alpha here, alpha over 2 minus half of sine of alpha by sine of 5. Delta has not been given, beta. We have to adjust this alpha with this here. See, ये inclination जो यहाँ पे होगा, you have to adjust it here. Basically, what you're doing is you're increasing this itself, isn't it? Okay, so that was backfill is homogeneous and granular material, failure surface assumed to be plane. These are the differences between the Coulomb and Rankine's theory. Rankine's theory is simply just a simplified version of Coulomb's theory. Next time we will do some questions on this. I think that's it for today. Is that fine? Okay. Thank you very much. हाँ भाई